Okay, we are now going to dive into the topic of storage as a grid component. Leading off will be Jeff Taft. Jeff is with PNNL. He has the dubious distinction of being the first power forward participant to participate in all three phases, which means you are like a power forward Jedi Master. Now we dub you Power Forward Jedi Master Jeff Taft.
All right, well, very good. It's good to be back here. And so what I'm going to do for the next few minutes is see if I can help provide some concepts that will help you get a handle around all the things you're going to hear about with regard to storage, and introduce this concept of thinking about storage as a distribution level grid component. I was listening to some of the discussions yesterday from Power Forward while I was doing work, and I think it was David Owens was asking some questions, and he was saying things like, how do we use storage? And then he had said at one point, what is storage? I'm actually going to deal with that a little bit because I think that will be helpful, and then I'm going to show you a few ideas on how we think about storage when we do the grid architecture work, and get to the idea then of what does it mean for this to be a grid component. So if I can work the technology. If you look at the things that constitute storage devices, this gets technically deep in a hurry. And if you look at the second row there, you see a bunch of different kinds or types of storage, and you go deeper, there are various technologies. If you try to deal with all of that in the type of things that you're doing, it becomes really unmanageable to have to sort through all of that stuff. But the good news is we don't have to do that. We can actually deal with an awful lot of this in a different way, and it's the way that we handle it typically in the grid architecture work. So let's clarify some things a little bit here. We're going to talk about electric grid energy storage, and what it is a function to absorb energy from the grid, retain it for some time, and then apply it to some use. And by the way, lately, some folks have started to use fuel stockpiling as if it were storage. And we hear people talking about grid storage, but what they really mean is piles of coal or tanks full of fuel and so on. That is not what we mean by grid storage. Fuel stockpiling may be a useful thing to do for various purposes, but we're not going to use that as part of this because that really confuses the issue and what we're trying to talk about. So the things that we really do with it, and you've heard some of this already, is use it to provide certain kinds of services to the grid. And the other thing that you don't hear as much about, although it's implicit, is decoupling volatilities between sources and loads. We'll talk about that in more detail in a little bit, because I think that will help you understand a lot of the uses that you would put this to at the distribution level. Now I'm going to introduce two more terms, and these are not terms that you would typically find people using in the storage industry, but we use them in the grid architecture work because these ideas will come up time and again, and it's important to be able to separate them. So we divide storage into two kinds. The first kind we call reflexive, and what that means is energy comes from the grid, goes into storage and gets retained a while, and then goes back into the grid in the form of electricity again. The other one we call transitive. Energy comes from the grid, goes into storage, and then goes to be used in some other manner. You'll hear both of those in terms of storage. They're both legitimate ways to use storage, but they have different implications for what they're doing and how you would apply them and how you would even think about regulating them. For the reflexive version, there's a kind of an indirect path as well that I didn't show here, and that is where you take electricity from the grid, put it into some form of storage, and that storage may be something that you can use to generate electricity from. And then so in a roundabout way, you go back to the grid. So I'll give you an example of that. You take electricity, you pull it off and you use it to generate hydrogen. And you keep the hydrogen somewhere, and then later on you burn the hydrogen and run a generator and put electricity back in the grid. So that's still reflexive because it goes direct back to the grid, but it's kind of a roundabout way. The transitive way, here's an example of that. You take electricity from the grid, you use it to make ice. You use the ice later on for air conditioning. So it never goes back into the grid directly. But you'll find people talking about storage, and they'll be talking about things like making ice or preheating buildings and so on. Legitimate forms of storage, not quite the same as that reflexive thing, which is the thing that we'll focus on a little bit more. Instead of worrying about all the details about how storage works, when we do the grid architecture work, and I think this will be helpful here, we concentrate on a handful of properties. The first one, really obvious, is how much energy can you store in a particular storage unit. The next two are related to each other. How fast can you put the energy in? How fast can you take it back out? Why do we split those apart? Because they're not always the same. Some forms of storage, one is faster than the other, and sometimes that matters. After that, if you just keep the energy in storage for a while, it's going to leak away. How fast does that happen? And sometimes you need to think about that. How many times can you store it and discharge it? Charge it up and discharge it? What kind of efficiency do you have round trip, and over what kind of time scale does it work? So if you only think about those kinds of things and not worry about what's inside the storage unit, this gives you a pretty good handle on an awful lot of what you need to know about thinking about storage from the standpoint of what it can do for the grid. There are a lot of uses that people have thought about for storage, and generally when it's connected at the distribution level, this is included in what we mean by distributed energy resources. It's not always connected at the distribution level. And because of this approach to thinking of it as something that supplies grid services, we've had the view quite a bit, and you heard a lot of it even today, of treating it sort of like an ancillary device to the grid. And the question of what constitutes services to the grid used to be a small thing, and now it's gotten a whole lot bigger. There's some verbiage here, it's probably too small to read if you're far away, but FERC originally defined what was meant by grid services, and it was a handful of things that were intended to facilitate the transmission of electricity from the producer to the consumer, so the delivery of electricity. That's really grown in recent years, especially with the proliferation of distributed energy resources. And so the list of things that are now considered to be grid services is pretty long. If you decide you want to dive into that, there's a place you can go to get a catalog of these things. It's all organized into groups and is commented and so on. That's on a website that's easily available. And it's gotten to the point where there are more than 40 of these now. It's not the original FERC definitions. It's a great deal more than that. But when people talk about grid services in the context of distributed energy resources, in the context of storage, they can mean any subset or all of those. And storage is unique in that it can do so many of these and can do a great many of them more or less simultaneously. This is another example. This is from Southern California Edison, and I adapted this from some work that Paul DiMartini did, in which they categorized a whole bunch of these services. And again, storage pretty much applies across the board here. Well, sorting all of that stuff out gets to be pretty complicated too. And the traditional approach, the common approach, is to think about that in terms of what we call value stacking and market monetization. So where there are organized wholesale markets, there's a lot of attention to DER services in general, but storage in particular. And you will see people thinking about how to put together a variety of different services and perhaps get paid individually for each one. That's led to some considerations about fragmentation of the market products at the wholesale level. There's a lot of discussion in some jurisdictions about the idea of markets at the distribution level for distributed energy resources in general and storage in particular. There are no such markets like that yet. And then that leads to these questions of another version of value stacking, which people are interested in being able to bid services for storage into the wholesale market and into a DER distribution level market as well. But a lot of this has been focused around the idea of market monetization of services, and what we're going to talk about is another approach to thinking about that at the distribution level. One of the reasons for that is this model, and this is something that I adapted from, again, from some work from Paul DiMartini, in which he was thinking about, so how does the value that's generated by DER in general and storage in particular accrue to different receivers of that value? That includes the customers, but also different parts of the power system. And one of the difficulties here for distribution is that actually not that much of it accrues at the distribution level to the distribution utilities. And so when you think about how is this going to be paid for, how is it going to be incentivized, there is the question of the distribution utilities' role in all of this. And understanding this issue about how value accrues is probably an important thing to know there. So maybe there's a different way to think about it. The question is, where does it fit into the grid? There's an awful lot of focus on the bulk energy system. And in fact, in the discussions that I heard today related to storage in EVs, I heard a number of things about benefits essentially to the bulk energy system. There's an awful lot about behind the meter storage as well, including mobile storage. But what we're going to focus on is actually something different. We're going to focus on storage that's connected at the distribution level but is not behind the meter. And that's a little bit different maybe than most of the discussions that you typically hear, but it's an emerging idea, and I think you'll hear more about this later from some of the other speakers as well. So what does this mean to treat it as a distribution grid component? Well, typically what it means is that we would want fast, what we call bilateral storage. If you think back to those 7 key properties, the bilateral storage part means energy goes in and out, so this is reflexive. Fast means it's quick in either direction. So that means kind of 3 parts to it. Some form of storage technology, and we're not specific about the nature of that technology. There are several that can apply here. Advanced control mechanisms to make it do all the things you want to do, and a very flexible kind of interface. So there's sort of 3 parts to that matter when you think about it in this particular form. Now, you may recall in one of our previous sessions, we talked about the concept of platform. I heard the word platform today, so even though it was the 2017 Utility Word of the Year, it's still pretty popular.
Ohio's behind always a little bit. I'm just kidding.
By the way, right now, the word that's in the running for the 2018 Utility Word of the Year appears to be resilience. That's the early leader in that.
Shocker.
I'm not sure if that's going to turn out to be the long run, but right now, there's some votes for that. So in the DSPX work that we did, we thought about how to define a platform concept for distribution utilities, and the diagram that you see there is an extended version of one of the diagrams that's in that work. And you'll notice down at the bottom, you remember we talked about this idea of the distribution grid itself as a platform for delivery of energy, for energy transactions. And what I've done there is I've indicated some of the key physical elements of that platform, and you'll notice that one of them is in fact now listed in here, is storage. That's not typically the way we've thought about storage. In a lot of places, the distribution utilities haven't been able to do this, and what we're suggesting is that this is an emerging view of storage, that it can in fact be an element of the distribution grid as opposed to something behind the meter, or as opposed to something that's attached to the system as an ancillary device in some manner. So why do this? We have changes occurring in the fundamental behavior of our distribution systems for a variety of purposes, and those changes are leading to volatility of both sources of energy and loads of energy. Volatility means, lots of time variation. So they're not as well behaved as they used to be. And we have this interesting situation with our distribution systems. Unlike other kinds of complex systems, we don't have any buffering capability in distribution typically. At the bulk system level, we have some flexibility in terms of capacity, but at the distribution level, not really. So that results in a certain lack of resilience. Oh, there's that 2018 word of the year. I knew it was going to come up. And we need to think about that in the connection with how these systems are going to operate going forward if we expect that trend is going to continue. And the volatility comes from both directions. It comes from the bulk energy system, when there is a lot more, a higher proportion of variable energy resources, wind and solar there, and it comes from connection at the edge of the distribution system when we have, connected rooftop solar, and we have more sophisticated behavior on in terms of loads and their ability to be controlled in various ways. So the volatilities can come from both directions, and those create a problem when the system that's in between them, the distribution system, doesn't have much ability to deal with all of that. Well, energy storage, which has not till fairly recently really been available, is potentially the thing that can help us with that. So why does this matter? Complex systems everywhere else have some form of buffering, and it's true in communications, it's true in logistics, it's true in water and gas systems. They go by different names, but there's always some form of buffering. And what they do is take something that's uneven and choppy and make it possible to smooth it out so that it becomes much better behaved. We do this all the time in communication systems when we have irregular flow of data and we want to deliver a smooth result, like say video, like for the millions of people watching the webcast here today. It's remarkable that we have not had that in distribution systems, but that's because we didn't really have the capability or the technology to do that before. And that's what is becoming available now that would be something that we would think about adding to distribution. It gives us a kind of sponginess or springiness that we don't have, and that makes it resilient to a variety of disturbances, and the sources of the disturbances, as we have discussed, are becoming greater all the time. So lack of that sponginess or springiness is kind of a vulnerability in the resilience sense, and we can address that by putting that in as a core capability of the distribution systems. So that's the missing shock absorber, if you will. And a way to think about that is to say, you know, if you had a bicycle that had solid wooden wheels and the seat had no springs, driving down a smooth road, not that bad. Drive it down a cobblestone road, not so good. If you are going to drive down that cobblestone road, you'd like to have that sort of resilience built in. And this is kind of the analogy to what we're talking about here in terms of operation of the distribution systems. So what do we mean by that in terms of operational functions and resilience functions? Well, we've already talked about variations caused by things like solar and wind. But we also can think about that in terms of matching up sources and loads. And, you know, with demand response, we talk about load shifting in order to make things run more smoothly. Well, here with storage, you have the option to do also generation shifting. You know, because the problem with variable energy resources is that we can't dispatch them. They generate when they generate. And maybe that's not always best matched to the loads. So there's a lot of effort in trying to figure out how to match those up. Well, storage can actually help you do that matching. It's the buffer that evens out those things. In terms of things like resilience, you can think about it helping ride through on outages and so on. Give you the electrical equivalent of what they do in the gas industry with line packing. In other words, if you have storage dotted throughout your distribution system and you know a big storm is coming, load up the storage, charge it up, and then when there are outages, use that storage to help you ride through those things. We don't really have a good way to do that at distribution now, except with distributed generation, if people have, you know, generators, backup generators, and so on. Here's another view of this: defense against edge-based volatility attacks. What does that mean? Well, one of the ways potentially to attack the grid is to manipulate the loads synchronously. In other words, get a hold of a lot of loads and start turning them on and off. That didn't used to be much of an issue, but in the course of, you know, the proliferation of IoT and all the stuff that's going on now, that's actually a potential problem. Well, so that's just more volatility at the edge, and so you could easily defend against that if you have a certain amount of sponginess to adapt to that. So you can actually think of this, in addition to everything else, as a kind of defense against that sort of an attack. And then, of course, using it for operational support for the things that you need to do just to make the distribution grid work well: volt-var regulation, stabilization, support for system integrity, even black start. I mean, the APPA folks have a report out now on the use of storage in their utilities, and one of the examples is using it for black start. So there are a variety of things that you would just consider operational issues and resilience issues that this can apply to, in addition to supplying the services in a way that people usually think of, and in addition to the behind-the-meter functions that people would use it for. So there are a couple of paths to thinking about value for storage, and the traditional path that we've talked about has to do with thinking of it as supplying grid services, and that's really aimed at reliable delivery of electricity. And the typical model for that is it's kind of an auxiliary component. Maybe we have a market monetization approach to dealing with those services. Another path for distribution for storage at the distribution level is to think of this in terms of core components and resilient operation of the grid. So it's more nearly focused on internal characteristics of the grid and making it perform well for the consumers. And in that case, you may think about that as a grid component and consider other options for how that would be paid for. This table comes from the DSPX work, and it talks about a number of different approaches that are available to think about how you treat expenditures. And if you look at the second one in particular there, that's a way that might be appropriate for some aspects of use of storage if it is in fact treated as a core grid component, an element of that distribution grid as a platform. And the idea here is to have, more tools in the toolkit to think about how to do this and enable it, because when we think about the accrual of value that I showed you, and the fact that there are not actually any distribution level markets, then the question is, how do you get that to work for distribution if that's where you want the storage to be deployed? So why would you want the storage to be deployed there? You could say, well, let's just let storage develop in terms of things like electric vehicles and behind the meter. Let's have market mechanisms and let those storage services be bid into those markets. But the problem with that is, in terms of things like resilience and so on, that doesn't give you firm design ability. That means you don't know how to get that to put the storage where you want it, when you want it, in the amount you want it. I mean, if you think about distribution planning, that's typically how things are done. You figure out what capacities you need and you put them in the right places at the right time. Well, if you're going to depend on this sort of organic development of these things because they're going to be bid into a market, you don't have that much control over them, so maybe you resort to procurement methods and so on. But if you enable the distribution utilities to actually employ storage themselves for these delimited purposes of internal operations and resilience, then you can have that firm designability issue and that ability also to firmly dispatch it. So storage can address a problem that we have that's developing, and that is that we don't have buffering capability. That didn't used to matter too much. It matters as we see more penetration of volatile resources and more controllability, especially remote controllability of loads. You can delineate a set of purposes and functions for storage that apply to that operation and resilience aspect of the grid. That is not to say that you would not have storage available to be bid into wholesale markets or to supply grid services. That's sort of a separate issue in a sense. But there may be better ways than market mechanisms to get this kind of capability that improves the operation of distribution grids. So hopefully what I've done here is give you some ways to kind of categorize and think about storage and separate out a few issues, and then think about the issue of what does it mean to treat storage as a grid component as opposed to an ancillary type device. So I'll stop there.
Thank you, Jeff. I think what we'll do is we will hear from all of our panelists, and then we'll do questions for the collective, if that's okay with folks. And I'm very sorry we got off track a little bit time-wise, so if we could do our best to push through presentations, and so we have a lot. This is a very inquisitive body. We have a lot of questions, and so I'm sure we'll have a lot of questions for you as well. But let me take a second and introduce our panelists. Kaun or Kaun?
Kaun.
Ben Kaun, Program Manager, Energy Storage and Distributed Generation from EPRI. Tim Ash, the Market Director, U.S. East Fluence. Okay, very cool. A Siemens and AES company. Davion Hill, Energy Storage Leader, DNV GL Energy Americas, and Scott Osterholt, Director of Grid Modernization, AP Ohio. Scott, we've spent some time with you before in Phase 2, so welcome back. So, Ben, the floor is yours.
Thank you very much. Appreciate the opportunity to speak here. So, I'm going to try to lay out a groundwork for some of the storage technologies applications, and then share some of the experiences that we've had working on energy storage projects and some of the existing and continuing challenges that we see in energy storage. So very briefly, EPRI is an independent nonprofit, non-advocacy research organization. We work collaboratively with a number of stakeholders, including utilities, the industry, and the other research community. We have an energy storage program, which EPRI's been working on for 30 or 40 years now. We work toward this vision of safe, reliable, affordable, and environmentally responsible electricity. In the energy storage and DG program, we're focused on technology evaluation, developing new analysis methods and tools, integrating technologies in the grid, and working with the industry to advance some common definitions and approaches for energy storage. So I'm going to go fairly quickly, as requested, over storage technologies, the applications, the challenges and research priorities, and then I'm going to leave you with a few of the publicly available resources we have that may be helpful in the future as you plot out your path with energy storage in Ohio. So quickly on the technologies, Jeff showed this to some extent, but basically energy storage takes electricity in from the grid or from another source, stores it, loses some of that energy in the form, usually in the form of heat, and then the electricity goes back into the grid. This is the typical way of thinking of it. As Jeff indicated, there's some wrinkles on this. There are some we'll say non-battery or non-electric to electric technologies. Some of these technologies also take input fuel and convert it to electricity out. Some of them can also have thermal or fuel outputs as well. So I think it's important to recognize that storage is not just batteries. It is a kind of a whole family of energy conversion and storage technologies. The general categories of energy storage, there's four big ones: the electrochemical, or the batteries that we hear so much about today. Electromechanical, or essentially turning electricity into some sort of mechanical form of energy and then back into electrical. Electrostatic, which is essentially turning holding charge in an electric field or magnetic field, and thermal, which electric to thermal or and back to electric, or just to some sort of sensible heat or cooling that might serve to support another process. So one of the key areas that energy storage technologies get kind of the distinctions that we see are often the discharge duration and kind of the scale of energy storage. At very short durations, storage may be helpful for issues of power quality and frequency. Then as you get into the medium durations of minutes to an hour, it might be energy imbalance or congestion. As you get into hours, it's often looking at things like daily peak load management. And then when you get over 10 hours, we start talking about seasonal shifting, weekly shifting, basically storing excess energy and bringing it to another time in space. So these two dimensions, if you go down on the bottom on this y-axis here, we have 1 kilowatt at the bottom, 1 megawatt in the middle, 1 gigawatt at the top. So basically from quite small from a grid perspective to quite large from a grid perspective. Some technologies are more modular than others. They can be built in smaller packages. Others cannot. They really need a large scale to get started. And then some technologies have sweet spots that are very power oriented or very small amounts of energy bursts, and others are not so good at taking in and putting out energy at a fast rate, so they're more appropriate for longer, slower charges and discharges. In the bottom left quadrant, we have things like electrostatic, supercapacitors, as well as flywheels, really good for the seconds to minutes time frame. We call them short duration technologies. At the other extreme, kind of up and to the right, we have some bulk energy shifting technologies like pumped hydro or compressed air energy storage. These are really very large scale systems that don't make sense. You're not going to have a customer sited pumped hydro plant or something like that. These are more appropriate for very long durations, site specific. And then in the middle, we have a lot of different battery and thermal type technologies that can be different scales of modularity. So there's a lot of focus right now in energy storage on this middle range of what I have here, from the 0.1 hours up to 10 hours. These are a lot of the applications we're looking at, things like T&D, congestion, peak load management. And if you look at, depending on the size of the technology of these different batteries or thermal technologies, some of them make sense. They're modular enough to be individual cells. You can build them into very small packages, like obviously lithium ion can be in your pocket So there's very small cell capability there. On the other, in the blue space here, flow batteries or sodium sulfate. Those are not quite as modular. They're semi-modular, but not something you're going to put in your pocket. One of the other things I want to point out about this slide is that lithium-ion has been a very attractive technology in part because of a very wide range of potential discharge durations from a few minutes to charge and discharge the full lithium-ion system up to several hours. So it really covers a lot of the sweet spot of what's being looked at currently as needs for the grid. There are a number of other attributes of merit besides just the power and energy capability of energy storage. One is the energy or power density. That basically impacts how big or small the overall project is going to be. And I'll step back to say, it's really not just the technology, it's that whole integrated solution of all the components that you need to keep in mind to understand if an energy storage project makes sense. The cost structure is important, of course. Where is it going to cost a lot more to add extra energy or extra power? The efficiency, the toxicity, flammability, or corrosiveness, the degradation characteristics, often looked at cycle life or calendar life. The technology maturity, how ready are users to incorporate these technologies into new products, and then geographic requirements. Certain technologies must be placed in certain characteristics, like in order to do a pumped hydro plant, you have to have the right kind of geography and topography to do that. And some are more modular and more flexible in how they can be sited. Despite this whole landscape of technologies, I think it's important to recognize that lithium-ion battery systems are really moving fast right now. They've been driven by tailwinds of consumer electronics and electric vehicle manufacturing scale-up and R&D investments. So they've achieved over a 50% cost reduction in the last 2 to 3 years, with that trend continuing. About 98% of all new deployments in 2017 were lithium-ion based, basically we think this one's an important one to watch, at least for the next 5 to 10 years, while the energy storage market is kind of getting its footing, and we're trying to understand where these things are going to end up. So I want to pivot and talk a little bit about the applications now. I like to think of it as storage as an asset with many potential moods. It can mimic different types of other assets that are often seen on the grid, depending on what it's doing and how it's being controlled. So the first way that we often think of first is the capacity resource. It can take power from energy from one point of time, move it to another point of time, often called peak shaving. This can be useful for both generation level constraints as well as T&D level constraints. So we think about non-wires alternatives or complements. It's also a flexibility resource, as Jeff emphasized. One of the nice things about storage is that it does have the ability to use both its charging and its discharging states, and moving flexibly between those states to support ramping requirements of the system, either because of load variability or renewable variability and uncertainty, and move much more so than the existing generation fleet is capable of. It's a reliability or resiliency resource. It's a reservoir of power, or of energy waiting, potentially, if it's configured correctly, to provide backup power to support microgrids, or, as mentioned, black starting a resource in the case of a blackout. And then finally, energy storage has advanced power electronics on board, so it can do dynamic 4-quadrant kind of operation and deal with things like voltage variations quite readily, without even necessarily needing to tap into the reservoir of energy that it has on board. But these capabilities come with the energy storage product. Energy storage can be put in a lot of different places at different levels of the grid: transmission level, distribution level, or at the customer site. I lay some of these out here. It can be at a gas generator. It can be integrated to the transmission system as a standalone. It can be renewable sited. And in these different applications, it has, at this level, access to provide support that would otherwise be provided either by transmission assets or generation assets. It can mimic generation capacity, essentially by providing that peaking resource or resource adequacy for the grid, black start capability. It can be kind of a virtual transmission capacity asset if a transmission asset's constrained. It can move energy from times of low energy prices to times of high energy prices if you know, a more expensive asset's on the margin, and then as Jeff indicated, provide these different flexibility or ancillary services as well. At the distribution level, transmission and distribution have a lot of similarities in that they often have capacity constraints. On top of that, there is the potential to enhance power quality near the point of use. So energy storage may be able to help keep the voltage in bounds, essentially, so power quality is higher, particularly for sensitive customers. And then that backup power or microgrid type capability is also possible. The other thing I wanted to emphasize for distributed storage is that it also has upstream transmission impacts. And depending on how you control the storage, that can either be a cost or a benefit. Energy storage does not have a specific standard duty cycle like solar. You know, it doesn't just go when it feels like going. Somebody tells it to go. So it's important to recognize that, you know, when you generate at the edge of the grid, you're going to have upstream impacts. And then finally, it can be at the customer. Usually customers would use this for savings on their bill if they have a time of use tariff or potentially demand charges. They may also use it for power quality or backup. And once again, it's important to recognize upstream impacts will happen, whether intended or not, and depending on how those assets are being used, that can either be a cost or a benefit. The other thing to be aware of with customer-sited assets is that there's multiple cost-benefit perspectives at play. There's the perspective of the adopting customer and their pros and cons, as well as the general ratepayer and their impacts from the adoption of other customers. So I'm going to go through just 3 kind of quick research priorities from our experiences working with energy storage in the last few years. The first one is how to analyze it. Energy storage has some unique attributes. It's limited duration, unlike many of the other assets that are on the grid. What I did last hour has impacts on what I can do this hour. So it's important to be able to incorporate that in any models that need to be used for planning and operations at the utility. It also has some of these new capabilities like flexibility and dispatchability, which are maybe not part of, for example, the distribution asset tool set. Another point is you'll hear probably a lot about value stacking. It's a compelling proposition everyone wants to do, to tap all of the values of energy storage to all the different stakeholders that it is capable of providing value to. But it is challenging because we need to understand if we're trying to create value. For example, we're going to build an energy storage plant instead of upgrading T&D infrastructure or instead of building new generation. There's reliability implications, so we need to make sure that the reliability criteria are being met before we try to stack on other benefits and squeeze more juice out of the device. Another related issue is that grid planning and operations tools have evolved with the processes, and those are historically siloed. So when you talk about crossing the T&D boundary and into generation and stacking all these benefits, we don't necessarily have a tool set that's ready-made for solving that problem. And then finally, rules and regulations continue to move with storage. We've heard a number of them FERC's making decisions, states are making decisions and targets, and as these happen, there's new technical requirements that may get laid over the top of storage, so it makes it a little more difficult to actually analyze if it makes sense. The second challenge is in energy storage performance and reliability. So we've seen very quick technology evolution in the last few years. The technologies are definitely capable of lasting longer. They're capable of being lower cost and higher energy density at the battery level in particular, but the available commercial asset track record is still very short. We only have a few years of experience of storage on the grid. So the overall degradation of systems is still an open question until we start getting available track records that where we can see what's actually happening, how systems are degrading under real world grid conditions. And that's all the components in the whole energy storage project, which can be rather complicated. And there's even a number of mundane issues that need to be looked at. I got a picture here on the bottom of rodent chews through a line and takes down a storage system. These kinds of things you don't necessarily get to experience them until you've had some experience operating them out in the field and maintaining the systems. The third challenge is grid integration. So similar to the analysis area, we need to be able to integrate these with grid controls so that they can support the reliability and enable stacked values. We may have heard about DERMS, or advanced distribution control capabilities. These are enabling technologies to support getting more out of, in particular, distributed energy storage systems. Another issue we've seen time and again when trying to do demos of storage is cybersecurity concerns, interacting with the IT department and issues with the vendor of the storage system wanting to get remote access and what the implications of that might be on cybersecurity. That's an area we're trying to work through. Other things like protection metering and communications, fire safety, and working with external entities. When you go into energy storage, it's there's no playbook in a lot of these cases, and so you're interacting with a lot of these stakeholders for the very first time. And so there's a lot of learning curve to try to get through a lot of these projects. So generally just trying to develop these implementation practices to take energy storage, which has moved very quickly on the technology side in the last couple of years from more of an R&D topic into an operations topic. And I just wanted to highlight one area where we're generating a lot of publicly available resources for through collaboration with the utilities and the various industry participants in energy storage is the Energy Storage Integration Council, which we started in 2013 with our program members. Also want to recognize that the Ohio utilities actually played a pretty leading role in putting this together back in 2013. The vision was we want energy storage to be as easy as buying a transformer, and there's a lot that it takes to get to that point where it's plug and play, easy to integrate. And so this is just a slide to kind of indicate that there's a number of tools that have already been published. One that probably could have 15 minutes on its own is the storage value estimation tool. There's a publicly available tool that we've developed over several years to provide some consistent methods to evaluating the costs and benefits of energy storage projects and be able to find and design and help to optimally operate those projects. There's also cost templates, tech spec templates, test manuals, and a number of other things to support some common approaches so that when vendors and utilities get together to try to do a project, there is some common documents that they can look at, a playbook, so that they can get on the same page and hopefully be 80% of the way to having a successful project. So I'll stop there. Thank you very much.
All right, good afternoon. First, thank you to the Commission for inviting us to participate. My name is Tim Ash. I'm a Market Director with Fluence, and I'd like to speak to you for the next 90 minutes or so. No, just kidding. Hopefully about 10 more minutes or so. about energy storage. Fluence, by way of introduction, is a joint venture between AES and the Siemens Corporation. We were launched in January of this year. We are the leading global energy storage technology and services company with about 500 megawatts of projects now either in operation or under contract. We're based in Arlington, Virginia, have deployed assets including here in Ohio. So I think my role today is to give you a little bit of a view from a company whose business is selling energy storage systems to utilities, to developers, to businesses for operation, ideally, here in Ohio. So first, the energy storage market is here, right? So you've heard a lot about the different use cases, some of the integration work that's going on. But to be very clear, energy storage is here. It's here being deployed by grid operators, by developers, by businesses, even residences from Australia to Alaska. Lots of different applications. Those applications make sense because the technology is proven and because the technology has made economic sense for going on 10 years now. It's accelerating because the performance and price of those technologies continue to decline. So the number of places that it makes economic sense just continue to grow. So I want to dig into a few of those specific use cases with you today. So again, our business is selling energy storage systems. So people aren't buying batteries, right? They're buying solutions. They have a particular problem they're trying to solve. They're trying to make more money, trying to reduce costs, or trying to provide some sort of insurance against an outage in applications like a microstarter or a black start. You've heard a lot of those today, whether it's batteries replacing traditional thermal peakers, whether it's providing backup power to a manufacturing facility, whether it's providing support to a microgrid. The one I want to focus on, though, and I think is going to be very relevant for Ohio for the coming years, is energy storage as a transmission and distribution asset in the grid. So there's kind of three specific cases I'll walk through at a high level, but what it really boils down to, storage as transmission distribution, is what you see at the bottom of this page. It really improves the reliability of the network and helps lower costs for all the consumers in that network. It's as simple as that. So in the first case, what we refer to as N-1 capacity release, this is really the case where you have existing steel or copper in the ground today that's just not being utilized. So citizens of Ohio have paid for that through their rates. In many cases, in some places in the transmission network in particular, there are links which have an operational cap set upon them, that has nothing to do with their thermal capacity. Because if we put too much power through that transmission line, for example, in the case of a contingency, that line trips offline, it could threaten the stability of the rest of the network. So say you've got a 2,000 megawatt line, we operate it at 1,000 megawatts to avoid that contingency issue. You can use energy storage deployed at the right place in the network, essentially to address that contingency and free up some of that existing capacity. What you see on the page here is a real-world example of that application. This actually comes from Chile, a couple of storage systems owned by AES in the northern part of the country. And what you see on the grid, the blue line is the frequency of the grid. That steep dip you see kind of in the middle of the page is where something has happened. A generator's tripped offline, you've lost a transmission link, frequency of the grid starts to drop. The energy storage systems, the green and red lines, detect that. They automatically begin injecting energy into the grid, support the load, maintain stability of the grid until the system is redispatched. 10, 20 minutes, maybe up to an hour. The energy storage system then goes back into standby mode, recharges, is ready to go for the next time. Again, this is a real-world example. The systems have been operating, the earliest one, since 2009. The benefit in this network specifically, they eliminated a whole layer of load shedding, so improved reliability. And the consumers in that grid save up to approximately $30 million per year because it's released a lot of lower-cost generation. So you bring more lower-cost energy through that grid to the consumers. The second case, a bit more applicable in the distribution level, is really what we call peak load relief. So as we know, the transmission distribution network is built to support the absolute peak load in that 1 hour over, say, the next 5 to 10 years. The thing that's challenging about that, as you see on the left-hand side of this chart, an example from Con Edison in New York, is that the number of times you actually hit that peak load is extremely limited. So in this case, 7 hours in the course of a year, typically at peak load. the top 1,000 megawatts in that network less than 30 hours over the course of the year. The way we normally address that issue, though, right, so we've got load growing, starting to run up against the thermal limits of that substation, of a transmission line. We build new substation, new transmission line. In some cases, it'll be very, very expensive just to meet those few hours per year. Instead, some cases it makes more sense, it's lower cost, deploy energy storage in the load pocket, support load during those peak hours, eliminate that thermal load on the grid, and now your existing infrastructure works. So again, it's lower cost. The other advantage storage can bring as well, as you see on the right-hand side, is its modular nature. You can deploy as much storage as you need when you need it. So you can match the growth in the load when it appears, instead of a big chunk you would normally do in a transmission investment. In addition, you avoid a stranded asset in the case where that load never materializes, which is happening in more and more places around the country. One real-world example happening right now, Fluence is commissioning a system for Arizona Public Service in the town of Pumpkin Center. Small community, end of about a 20-mile radial transmission line. The load there, again, during peak hours is starting to run up against the thermal limits of that line. APS found it was about half the cost to deploy energy storage there as opposed to reconductoring that transmission line. 2 megawatts today, again, it could expand if load continues to grow, or they can stop there if load remains flat. The last case for energy storage in the distribution network in particular is addressing reliability issues. So less a thermal constraint. One example I'm highlighting here is voltage stability or voltage flicker in distribution networks with very high penetrations of solar, for example. Cloud comes by, you get that fast drop in production and then the fast ramp back up. You can create some voltage flicker issues. In addition, if you have a lot of solar, for example, in a distribution network midday, low load, you get reverse power flows and again some voltage stability potentially. So deploy energy storage, it creates that shock absorber effect, absorbs energy to put back in as it's needed and address some of those issues. Again, you can help improve the reliability, potentially lower cost. You reduce wear and tear on the equipment, you avoid the need for investment in other infrastructure. Again, one example, real world from Arizona Public Service. They deployed two 2-megawatt systems in their grid, an area of very high penetration of rooftop solar. One of the systems sits at a substation, the second out on a feeder, and they're essentially coordinating the energy storage and the solar to help mitigate some of those reliability issues and avoid the need to upgrade infrastructure. And the last thing I'll highlight has been touched on already today, but this idea around value stacking or multiple use cases. I want to highlight one issue for the commission that I think commissions around the country are really seeing and dealing with now, is the flexibility that energy storage provides allows it to become a multi-use asset, right? So this peak load reduction application. If you look on this page, that kind of smooth line towards the right-hand side of the page, afternoon peak, energy storage is deploying energy to support peak load, avoid the need for that infrastructure upgrade. The other 20 hours of the day, it can do a lot of useful things, and in particular, people tend to think about participating in the markets, whether it's providing ancillary services such as frequency regulation or spinning reserve, providing on-peak power. The reason you want to do this, instead of a 10% utilization asset, I now am at 96%. It reduces costs to the consumer at the end of the day. This, of course, runs up against a lot of different market rules in various states and in various ISOs, RTOs. But it creates real value. The capability is there. Systems are doing this today. And I would expect that PUCO will be looking at these soon. Thank you very much.
Appreciate the opportunity to speak with you all today. I'm local. I'm a Buckeye, and it's an honor to be speaking with all of you and be talking about this opportunity in my home state. Usually I'm in other states talking about this, so it's nice to be able to be here. Appreciate it. A little bit about DMVGL. If you're not familiar with us, we're the world's largest renewable energy consultancy. We have our main business is independent engineering, which is what that means is we're the independent engineer consultant that comes in during energy project development to work on behalf of the bank to make sure that the technical specifications for the project are accurate and that they're going to uphold the contractual guarantees that the suppliers are giving to the bank and the developer as they build the project. We have about 95% market share in wind, over 50% market share in solar for that, and I'd estimate about 50% market share for storage these days. Some things that I really want to emphasize today is that storage today is commercial. It's off the shelf. It's making money. It just takes some work to define the business case and which markets you're playing in. But the markets are opening everywhere, and I'll show a little bit of a timeline of policies, different states, and with some of the FERC rulings that have come out, what that means for the market. There's also some interesting things to consider in terms of the electricity markets today. We've been looking at a scenario where electricity demand has been largely flat, and that has been due to the fact that we're getting more efficient at producing electricity. Usually you see energy and GDP growing hand in hand together, and our GDP is growing, but electricity demand is flat. So we're seeing some decoupling from that, and that's largely due to the success of efficiency, at least in electric markets. There are still, though, costs that we need to address in terms of upgrading the grid, and we're seeing that the peak to average load ratio is increasing. So even though you've got flat electricity demand in areas where you do have peaks, those peaks are, the ratio from the peak to the base load is getting bigger. So you need to address that somehow. And I would have never thought this would happen 5 years ago, but today renewables are the lowest cost energy in capacity markets. So what that means is if that's the lowest cost, that means that's where everything's going. If it's going that way, that means you're having more intermittency, and that's something that needs to be resolved with potential for decreased reliability. Lots of discussion today on EVs. I'm not going to touch on that too much, but that's a significant load. So if there was something that would start to increase the load again and make that flat electricity demand curve change, it could be EVs. We have about 40 quadrillion BTU of oil that we use to support transportation. If you put all that into megawatt hours for EVs, you'd be looking at something on the order of 11,000 terawatt hours. And that's about 1.3 times the size of our current grid today. Not that that's all going to happen and go directly to EVs, and there's some timing issues to resolve in that in terms of when you charge, but just to give you a sense of the order of magnitude of what we're talking about in terms of demand. And the last thing is resiliency. If you look at some data from NOAA, you'll see that there's an increasing frequency of billion-dollar storms. You've probably seen that data before. That just means hurricanes are hitting more populated areas, and when they hit those populated areas, it causes a lot of damage. And there's a need to provide backup power in New York in particular after Hurricane Sandy. There's lots of discussion about resiliency. A lot of people had solar on the rooftops, but they couldn't use it because those inverters are grid sensing. When the grid's down, it doesn't deploy power. So you couldn't microgrid with the solar. So what do? If you had storage on site and you could microgrid, you'd be able to have a place of a microgrid island of power, and then you could use that as a launching point for a lot of emergency services. So storage is a common solution to all these issues that I just brought up on this slide. I want to address some markets that are present now, active. When we get involved in projects, we're getting involved in projects because somebody is about to finance them. So that means that there is a bankable business model, and we're there looking at it to see how the business model works and how the technology is supplying that business model. The markets where we see projects being most active, there's still projects happening in PJM with frequency regulation to serve the Reg D market. One of the biggest businesses that we have today is out of California due to the resource adequacy payment that is a result of the 1.3 gigawatt storage mandate. I've been told by Janice Lynn at Strategen that I shouldn't call it a mandate. I guess it's a target, but I'll get more into that later. Ontario has an interesting two markets that are evolving there. One is the global adjustment charges market, which is essentially a way to pay for addressing the peak and deferring upgrades to address the peak. And there's also an active frequency regulation market there. In the UK, a frequency regulation market just opened up, modeled itself a lot after PJM. And in South Australia, a lot of big projects going in there for storage, and there's tariffs there to address both reliability, peak needs, and eventually ancillary services. In the next 1 to 2 years, this is very interesting to say because I've been in storage for about 11 years, and there was a long time in the early days where we were saying, boy, if that happened, that would be really amazing. That'd be interesting for the market. No more of that talk. There's some certainties that are going to be coming out here with FERC's rule from 841. We know that there are going to be tariffs in place for storage on all the ISOs within the next 2 years. That's huge for the market. That means that there's a way to pay for storage. There's a way to make money with storage based on that ruling. New York will eventually release their VDER tariff, which is a way to pay for, among other things, avoided distribution upgrade costs. And that's part of the tariff. It's valued in the tariff. PJM will be opening a primary frequency response market. Don't know what the size of that will be, but PJM is in the middle of looking at that analysis. They've got a task force that's looking at that, and they're trying to figure out how to monetize that. That's bound to open up in the next 1 to 2 years. And the FERC NOPR, that the Notice of Public Rulemaking that instituted 841 still has a lingering piece on it related to DER participation in wholesale markets, and storage will have a play there. And we're also seeing a bunch of activity in Arizona and Nevada, Massachusetts, and likely the rest of New England. So almost always a winner for storage. What's the value proposition for storage? If you can defer grid upgrades. Every time we do an analysis, we usually see transmission deferral or distribution deferral ranked up there at the top of what the value of storage is going to be. A couple examples here. One of them is behind the meter, and one of them is a utility scale solution. We are working with a college. The college has a growing load. They've done a great job recruiting, and they've got a lot of students coming in. But they know that they're going to have to upgrade their distribution network, and it's going to cost them about $10 million in switchgear upgrades to do that. And they started wondering, is there anything that we could do with storage here? And we did the analysis for them and found out that about $4 million in storage would achieve the same thing for them, and they could defer that $10 million investment. So that's one way for them to pay for that. In addition to that, they can also shave their peak and avoid demand charges. So 2 value propositions for them. Con Ed has a great example with the Brooklyn Queens Demand Management Program, or BQDM, where they are looking at investment in wires or substations that would cost them billions versus they could invest millions in storage and save themselves a lot of money. So being able to defer those upgrades is valuable to them. The main takeaways from that are that storage deploys faster and cheaper. It's very modular, as Tim showed. The permitting process is typically 4 times faster than a gas peaker, and you don't have to worry about a lot of the environmental impact study requirements because you don't have emissions to worry about. This slide is an attempt to show how stacked value streams are actually overlapping across the many different kinds of storage you hear about. You hear a lot about behind the meter, and you hear about utility scale, and those are all kind of not officially defined terms, right? So how do we put some color around those? The projects that we see today for behind the meter, a lot of them have a demand charge or time of use management function in them, and that's how they're getting financed. That's what makes them bankable. In addition to that, they are stacking that on some sort of direct or indirect benefit of a state policy. So take California, for example. The resource adequacy payment is a contract between the storage developer and the utility. And the utility pays them to be ready to deploy 4 hours of storage when they need it. That's one revenue stream. And then they independently sign a lease with the site to do demand charge management or demand charge savings, and that's a separate contract. You put those 2 together, and that's the combined revenue streams, and that's the business model. It gets financed because both of those are very bankable. The utility is a very credit-worthy off-taker. If you're a bank and you're looking at a contract with the utility, you don't question whether or not they're going to be there to make the payments on that. And demand charge management, as long as it's a understood mechanism and the reliability of the prediction of being able to shave the peak looks like it's bankable, then that's another considered to be highly bankable revenue stream. At the utility scale, you can see some overlap. There's a direct benefit from, say, a cost recovery mechanism. Again, the California Resource Adequacy Payment is a good example of this. But then there's also a financial benefit of increasing reliability, what storage can do, and then deferred upgrades. So if you can stack those 3 value streams together, we're seeing that in projects today. And that's something that's working for utilities. And then at the ISO level, the one that's sort of paved the way through PJM is frequency regulation with Reg D. But we're going to have future tariffs for storage based on FERC Order 841. And then we're also going to have a PFR market coming up here soon. You could participate in the capacity market today with storage, and it just depends on what energy you're using and how you're bidding in and what your strategies are for bidding in. But there's a way to play in that wholesale market as well. So you can see there's some overlap in all of these. When we have a market where distributed resources, whether they're large or small behind the meter, can participate in wholesale markets, you'll see these lines blur a lot more. I think we already went through some basics of storage, but generally you hear about costs of storage, and the only reason I'm putting this in here is to get some color on that. So you take battery cells and you put cells into modules, you put those modules into racks, and you put those in a container, and that's what an energy storage system looks like. We're seeing some differentiations on that model. If you take Tesla, for example, the Power Pack and Powerwall are sort of an intermediate scale modular architecture between 10 and 1,000 kilowatts. And all that design for that is to basically engineer out a lot of the balance of mass and complexity in the system and reduce cost. And so we're seeing a trend for that in the market. As mentioned earlier, 95% of the market today for energy storage is lithium-ion batteries. Most of our projects that we're getting involved in where we're doing the technical review, it's a battery and it's a lithium-ion battery. And the reason for that is that the cost of those technologies are going down so much. And the reason why is because it's coming from the automotive market. So the other 5% of the market that's not being addressed by lithium-ion, likely to be things like vanadium redox, perhaps zinc bromide, but for most projects you're going to see today are going to be lithium-ion, and those batteries are going to be batteries that you see in cars. And there's a very strong economic driver for that. This is how we've been tracking costs for the last decade, and these are real numbers. You can see that cell costs, back in say 2008, we were looking at lithium-ion cells around $1,000 to $1,200 a kilowatt hour. Today, they're being sourced for less than $150 a kilowatt hour. By the time you integrate them into modules and battery packs and systems, you add some costs to that, but people are getting smarter at that, and so the costs are going down there as well. You can see the red curve is the total system cost, and that was a lot broader in the early days, and now it's shrinking as time goes on because people are getting more experienced. So there's two projects to note. In late 2016, when AltaGas and Greensmith announced an energy storage project to be deployed in California to address the Aliso Canyon gas leak, that was an 80 megawatt hour project announced at $45 million. That comes out to $562 a kilowatt hour installed. And then the Tesla South Australia project that was done last year comes out to about $387 a kilowatt hour installed. Now you have to think about some other costs associated with development fees and things like that, but that is an indication of the market declining. And that comes from projects that are being deployed with automotive batteries. So just a thought experiment here. I'm not trying to promote any particular company, but if you look at just the Tesla Model 3 pre-orders and you think about what that means, if you say it's an average 60 kilowatt hour battery, the pre-orders represent 24 gigawatt hours of price negotiation power. So when people talk about different kinds of technologies being deployed on the grid, I have to look at this number and say, what's the future battery going to look like for the next 5-10 years? It's going to be a lithium-ion battery from the automotive market. This is why. You've got a lot of scale there, you've got a lot of cost reduction there, and you still have a lot of opportunity to reduce costs even further. We're pretty bullish on energy storage prices being in $200 a kilowatt hour range installed in the early 2020s. So that's important to know about. Cost is also driven by how you integrate the projects and how you build the projects, and the trend in the market right now is having an engineering, procurement, and construction company, or EPC, come in and give a turnkey solution. They install the system, they design the system, they operate the system, they provide the operations and maintenance package, and those systems are lowest cost when that EPC has a very good integrated supply chain, whether they vertically own all of those things in their own vertical integration, or they have very strong supply agreements with suppliers. Ultimately, that has to be connected to a battery supplier that's connected to the automotive supply chain. If that modular architecture is being shared with an automotive platform, that helps reduce cost even further. The automotive market in terms of batteries is about 10 times bigger than the stationary storage market today, just to give you an idea of that scale. Being able to optimize the balance of plant and implement construction and do that efficiently with contractors that they've worked with before, and then provide the service package that's got the controls, the ability to address future markets, performance guarantees, liquidated damages, O&M, augmentation and replacement costs, all that built into the contract. That makes the bank comfortable, that makes the developer comfortable, and that means that they can implement and operate that energy storage project for a long time to come. This is being somewhat templatized in the market as we speak. So we're seeing EPCs advance very quickly in how they are developing these contracts, both commercially and technically. And this is something that has evolved very quickly over the last 2 years. So from a commissioner's perspective, when you think about this, there's a market solution that's already out there that can do this. And I think that's important to notice and acknowledge. This is a cluttered slide, but this is the timeline of policies that have evolved over time. And I think what's really critical is you can see there's a lot more on the right than there is on the left, which means the activity is increasing. And we've got these FERC orders that just came out for 841 and what might come up for PFR. And I think a lot of that is triggering, I don't think we can predict the growth rate. We've seen hockey stick growth so far. There's these predictions that GTM has provided to the Energy Storage Association, for example. And they might be wrong. They might be too small. Once you open up a market where you've got FERC saying, here's a tariff, and that tariff is a bankable revenue stream, there's no reason to stop anybody from going out and developing storage projects. And as you've seen, we've got contracts already in place to go build energy storage projects. So you just are missing the energy revenue, the energy monetization. And once you have a tariff in place, there's nothing that's saying don't go. There's everything that's saying do go. And I think that's important to acknowledge. I already talked about some of that. One thing that's a good example, I think, to follow is what California did with the 1.3 gigawatt mandate. Essentially what they said is, look, if you're going to go do something in the market to build our infrastructure, it has to be cost effective, which is the mandate of a lot of public utility commissions. And they said in the bill, look at energy storage and evaluate whether or not it's going to be cost effective. And the utilities essentially said, hey, look, what we really need is resource adequacy. I don't care what it is, I just need resource adequacy. And that payment mechanism is what has paved the way for storage in that state. Storage turns out to be cost effective in a lot of different cases. And they've got a payment mechanism, which is resource adequacy. You put those two together, boom, you have a market. So that has been a very viable market. That's been a very understandable market. And that's what has grown a lot of energy storage in the US today. You can see a common theme tied to some of the other ones. We've got the desire to reduce greenhouse gas emissions. We've got the desire to address the peak. We need reliability, and we need to defer upgrades. That's all mentioned in this bill, and that was all California's mission. Nevada is looking at the same thing. They're doing a study right now coming from the Governor's Office of Energy in Nevada with some oversight from the Public Utilities Commission of Nevada, and they're looking for the same things, common themes: integration of renewables, greenhouse gas emissions, addressing the peak, reliability, deferral of T&D, and ancillary services. So they want to understand, how can this work here? Another important thing to think about from both Nevada and Arizona is they've had efficiency programs that have been very beneficial to them in terms of reducing their peak, but they're seeing that, is there really a reason to offer rebates on LEDs anymore, given that they're so low cost now? What's the reason to incentivize that? We don't really have another technology to help us move significantly beyond this in terms of efficiency. So what do we have left? Well, now they're looking at things like storage. How can you use storage under a rebate program? How could you address the peak with storage? How could you reduce overall peak loads and costs with storage? And so that's something that they're looking at. I mentioned that with APS. You can see in APS's integrated resource plan that they are projecting anywhere from 500 to 1,000 megawatts of storage in the next 14-year timeline. So it's important for them. I mentioned New York earlier. The VDR tariff has a direct acknowledgement of avoided distribution upgrades, and that's part of the tariff evaluation. Once that gets implemented, you would have a piece of that tariff that addresses the avoided distribution upgrade cost, and there's an expectation that storage will serve that. Similarly, Texas has made some movements to, the language in here actually looks very similar to FERC 841. We've got things where energy storage doesn't have to pay retail rates on charging, for example, and they want to be able to allow interconnection and streamline that process and make it exempt from transmission service rates. So those are some interesting barriers to remove, and hopefully will enable storage to grow in that state as well. I talked about Ontario. The IESO had put forward the global adjustment market, and this is an interesting one because there's a software component to this. Storage can be deployed behind the meter. It can address the peak of that load behind the meter, but it's doing so to meet a utility need. So that's where a behind the meter asset is doing a utility function. And that's really important to note. They placed a value on that. They did some evaluation studies to get that number right, and then they implemented that market, and that's a very significant growth market for storage as well. So in conclusion, the lessons that are learned here, the enabling policies are where utilities have a cost recovery mechanism on storage, like California resource adequacy, for example. Time of use demand charges, always an enabler for storage. It's a way to address that peak and put a value on that peak and therefore monetize it. The ISO markets, they're going to inevitably release more orders like this, like what we're seeing coming out of FERC. And so the state should align with that and be able to use their own utilities to align with that and get a mutual beneficial revenue stream and value. Reliability has value, and so that's obviously a concern for a lot of the public utility commissions. And being able to defer distribution or transmission upgrades, almost always a win. And if that can be shown, then that shows that there's a viable investment in storage. And so the main question, I think, if you put all this list together, is the way to look at it is for every dollar invested in storage, how much is saved? And there's a lot of different ways to slice and dice that, but it can work in a lot of different markets. And I hope the examples I showed you are useful. Thanks.
Scott.
All right, so I want to thank Chairman and the commissioners for having me again for a second time. Appreciate having the ability to kind of share our thoughts and insights on how we can move forward with energy storage and really drive benefits to our customers. My colleagues have done a great job of giving you very, very technical presentations. Mine is going to go a whole different direction. I'm really going to focus on, as a utility in the state of Ohio, how could we work together? How could we move energy storage forward? All right, so if it's okay, I'd like to go back to 2008, 2009. That's when we started our grid modernization efforts. And again, it wasn't the biggest deployment, but as you can see, there's a lot of different technologies. The reason I bring this up, if you look at the bottom left and kind of more at the bottom right, you'll see there's two technologies that we've been working on since 2008, 2009 that have occupied your entire day today. So again, our Grid Smart Phase 1 project was a learning opportunity. What we wanted to do is learn how we can move these technologies forward and bring benefits to the customers. So just recently, last year, we got ability to move forward with our next phase, we're calling Phase 2. The reason I bring this up is, when we move forward, again, we're looking at those benefits for the customers. For this project, for every dollar that we spend, we deliver $3 in benefits to the customer. So over a 15-year business case, that's more than $1 billion in perceived value. Those are the type of projects that we really like to move forward from a grid mod perspective. Again, it's not just projects. All the way to the top of our organization, grid modernization is important. Our chairman, CEO, Nick Akins, has numerously been quoted of 3 important things. 1, to modernize your grid. 2, to improve reliability. And 3, to keep your cost profile under control. So, and I'm going to talk about those 3 things today and how they tie to the energy storage market. From a grid mod perspective, this is some research that we found. You can see in the center there, Ohio, we're kind of a fairly dark blue. That represents 6 to 9 grid modernization actions taken. There's only 8 states that have more grid modernization activities taken, so that puts us in a fairly good leadership role. Things like Power Forward is going to continue to help advance these type things. From an energy storage perspective, so similar research I want to talk about. You'll see in this slide, Ohio is also kind of in that kind of relatively dark blue. This means on this slide that we have some energy storage deployments. You'll see that one of the things that we do not have is a lot of energy policy, a lot of demonstrations, a lot of research. You'll see that more on the coast, so that puts them in more of a leadership role. Things like Power Forward, how we could create some policy, how we can create some legislative actions to remove some barriers, will help the state of Ohio move energy storage forward at a faster pace, move us into more of a leadership type role. Again, my colleagues have done a great job of explaining the technology, the benefits. I only want to kind of highlight a couple of those. From our perspective, the 2 biggest benefits for energy storage for our customers are the increased reliability improvements and then the cost-saving opportunity. Again, those tie really well to what our chairman CEO is driving as our 3 core principles. On the right, we've heard a lot today about use cases, how we can use energy storage. From a simplistic standpoint, we narrowed it down. We have, on the right side of that slide, we have 11 different use cases. So as we kind of reflect and say, okay, for the state of Ohio, looking at those 11 use cases, how do we move this forward? How do we bring benefit to the customers? And we put those in kind of 3 pockets. The first one is deferred T&D costs. So those are things like your capacity improvements. So if we have a capacity need, so load growth or whatever else, if there is an opportunity to use a battery to offset a traditional T&D expense where that battery is a lower cost or a better technical solution, we think that the utility should have the ability to use that and move forward. Similarly, the second bucket is reliability. So again, there's pockets where we need reliability improvements. You look at those projects, how do you improve that reliability? If a battery can solve that at a cheaper cost or a better technical solution, again, that's something that the utility should be able to move forward. The third bucket there at the bottom, I'm calling the enhanced customer experience. And those are really just different types of things that we can do to enhance the customer experience. The first one I'll talk about is voltage. So customers often through their manufacturing process, they create their own voltage problems or they have very sensitive voltage issues that they want us to help them with. They can always solve those on their own. But what if they could work with the utility and together we could cost share, solve those voltage problems on the distribution side, then use that energy storage asset to solve other grid needs? That's kind of a win-win. The next one I want to talk about is community energy storage. So a lot of things you've heard so far today is big batteries. There's also an opportunity for smaller batteries. Moving those batteries closer to the customer's load provides the customer with more reliability benefits. It gives us, as a battery displacer, more options, more flexibility in how we do that. The next one I'll talk about is residential batteries. So utilities have long worked with customers to do demand response programs. So could you imagine a day when we offer the customer a premier service offering where we give them a battery? Obviously for the customer that gives them reliability improvement, but also as the runner of the grid, doesn't it give us some opportunity to use these batteries in a way to manage our grid? And then the last one I'll talk about is microgrids. So again, a lot of people talk about microgrids, it's a pretty trendy term. They're talking usually about a campus, something behind the meter. When we talk about it from a utility perspective, that's not what we're talking about. We're talking about in front of the meter. So what I always like to think about is big giant storm comes through, knocks out a lot of power. What do you want to have power after that storm? The critical infrastructure, things like emergency, fire, police, emergency management centers, maybe a place to get gas, maybe a place to get prescriptions. Those are the type of places that we're looking to say that's a good place to put a microgrid because that provides societal benefit. So in this case, a microgrid is just energy storage with an alternate energy or generation device so that you can sustain for a longer period of time to provide those services over that period of time that you're looking for. Next slide, I want to talk about the cost benefit. And this is a slide that I borrowed from EPRI because it really does a great job of kind of looking at the cost and the benefits. So on the left side of this graph, you'll see that there's a stacked bar graph looking at the cost of owning and running a energy storage system. Pretty straightforward. What's it cost to deploy? What's it cost to maintain? I'm sure we've all put one of these together in our careers. On the right side is another stacked bar graph. We've heard a lot of terms like yesterday we heard pancaking, today we've heard value stacking, and really this is a good representation of how you try to find all these different benefits and layer them until they're at a point where there is more benefits than there are costs. And in those cases, and the utility finds those sweet spots, we should be in a position to work together and move those type of energy storage systems forward. Talk a little bit about AEP Ohio's history or experience with energy storage. It's probably not widely known, but as of today, we have a 2 megawatt battery system in Bluffton, Ohio. It was installed in 2008. It's a distribution asset. Its primary purpose at the time was to defer a transmission distribution capital project. It's interesting to me to know 10 years later that we still haven't had to put that T&D project in place. The secondary benefit of this battery system is this area, Bluffton, Ohio, is served with a somewhat challenged at times sub-transmission line. So here you can also use the battery then to address reliability issues. And then as recently as last year, we had some of those transmission voltage problems, and this battery was able to retain and power the Bluffton area without any downside effects to the customer. So it's really a good example of how you can use a battery to island and serve both capacity and reliability challenges. I also want to talk about community energy storage. Again, as I mentioned before, community energy storage is typically, a smaller profile, typically 25 kW, kVA, maybe 50. And part of our GridSmart Phase 1 project, the Commission gave us approval to experiment with this technology. One of the things that we learned is, again, this could be a premier product offering in the future. So we experimented with things such as what we call equal energy allocation. So let's say that battery had 25 kilowatt hours in it, and that facility serving 5 customers. How do you ensure that every customer gets 5 of those kWh? And that's something that we were successfully able to complete. So kind of setting it up for that future opportunity to use it. I've heard there's a lot of interest in the AEP Texas, our sister company, and their recent filings regarding energy storage. And I'll talk a little bit about those. On this slide, you'll see the two use cases that they've been talking about and working to push forward. You'll see they're very similar to what I just talked about, a reliability and a capacity case. So start off talking about Woodson, Texas. In that case, AEP Texas was looking to put a 2 megawatt hour battery system, lithium ion battery system, in to resolve a reliability concern. As you can see, it was a $1.6 million estimated cost for the battery, versus if you were going to do traditional T&D improvements to resolve that reliability concern, you're looking at around $5 to $5.5 million in cost. The second use case, Paint Rock, Texas, which was a capacity issue. In this case, AEP Texas was looking to put up a 1 megawatt hour battery system. This was to resolve a load growth or capacity concern they were dealing with. In this case, the lithium-ion battery was estimated at a $700,000 cost, as compared to a traditional T&D investment of $6 to $17 million. So a pretty big difference there. So Texas did file for these as specific projects, but that was really just to get the conversation started. You might have heard that the PUCT did not approve it, but what they did is they're working to establish a rulemaking session to establish the rules to move these type things forward. AEP Texas is optimistic that they'll have the ability to have batteries for reliability and capacity in their toolbox to use. They're also optimistic that there'll be some set of criteria for when they can use it. They do not want to go back and ask and file for a battery every time they want to do one. So, and again, that's similar to the Ohio perspective as well. Due to time, I'll kind of breeze through this, but there's been a question about, does energy storage help you from a cybersecurity perspective? I'll start off by talking about a fact. I'm sure it's a fact that kind of scares everybody here, but the Department of Homeland Security has said that the energy industry has more cyber attacks than our peer industries. And again, that's why it's such a hot topic, right? So, everybody's talking about it, everybody's investing in it. So the short answer is, I think there are some ways that energy storage can help from a cyber perspective. And Jeff did a good job of laying this out as well. But again, if you're using batteries or energy storage and they're decentralized, if there has something happen, you have these other pockets of alternate resources that you can use to bring load back up. Think about putting those in places that, again, back to the critical infrastructure. Where could you put those that provide the best benefit in that type of situation? I'm going to skip over, cybersecurity. We have AP has our cybersecurity officer coming in to talk a little bit more about that. But again, this is a new technology that has a new processor. It's got a new, communication device. So anytime you have those type of things out in the field, you really have to pay attention to cybersecurity. And at AEP, we have a great team that looks at that for us. So to wrap this all up, I'd like to summarize how AEP Ohio could be a great partner and a great resource to roll out energy storage. So I'm going to start with number one, AEP Ohio and the other utilities in the state. Our main job is to keep the lights on for the residents in Ohio. That's what we do every day. So when it comes to needing additional capacity, load growth, when it comes to solving reliability pockets, that's what we do. If you put that in the hands of a marketer, they're going to optimize for themselves. They're going to optimize for their own financial well-being. And I'm not saying that that's a bad thing. I'm saying, though, if you want to have somebody that looks over the entire grid for all customers and for the best of the grid and best of all customers, I think that's what we do well. Next one, lower cost. So it might be counterintuitive, but if you think about it, you have 100 energy storage systems to deploy. If you have 100 different companies doing that versus one company doing 100, you have economies of scale, bulk pricing. As you deploy the projects, you get better at it and more efficient. Those all things are cost improvements. The other thing to think about, if you have 100 different people putting 100 different batteries or energy storage systems on the grid, you have 100 different interconnections to make. So you have all this stuff that has to connect to your back office system that you have to get integrated. All that comes at a cost. Cybersecurity, talked about that just briefly. Again, if you're rolling out 100 different battery systems, 100 different providers, now you have 100 different points at which cyber hackers can attack the grid. Those are new penetration points into the grid. So you got to think about how that cybersecurity aspect is. Next one is availability. So we as a utility, we're used to putting in assets that last forever. We're good at maintaining them. We're good at getting every last year out of them. So, I think Ben's slide was talking about, one of the challenges with energy storage is keeping them up and running. So again, we think as a utility, we do that well. Last one is regulatory oversight. Again, I think you guys have a vision of where you guys want energy storage to go. You want to drive those benefits to the customer. From a regulatory perspective, that gives you the ability to continue to make sure your vision is put into effect or executed. And I think that's a good way to handle that. So again, not saying that there's not a way that we all don't work together. I'm just saying there is a good opportunity for the utility to partner and move some of things forward for the best of our customers. Thank you.
Thank you, Scott. Questions? Who's got them? Christina?
Davion, for you, you mentioned some of the turnkey solutions that are available. Just in general, what's the timeline for getting those into operations? I know you work on the financing, so just kind of what's the range of timing for some of those projects?
We've seen it as short as 6 months. I think AES could also, Fluence could comment on this as well, but in the Aliso Canyon instance, that's a market where you already had a mechanism to pay for storage. And they saw the problem, they put out RFPs, and they had projects commissioned between 6 and 9 months from then. So very fast, provided that there's ease of access and things like that.
Yeah, that's right. I think we deployed one of the similar project in response to the Aliso Canyon event in just a little over 6 months. That was actually 2 projects, one at 30 megawatts, 120 megawatt hours. The largest grid scale energy storage system in North America. The second was a 7.5 megawatt 4-hour system as well, both simultaneously within that kind of 7-month time frame.
Jake?
Question primarily for Ben. We've heard a lot about the benefits of grid storage. You say that there are impacts can be cost or benefits. Can you touch on the costs briefly, just for the sake of balance?
Sure. So energy storage, once again, doesn't have a natural operating profile, so it all depends on who's controlling it and for what purpose. So, for example, if a customer or a utility is controlling it at the edge of the grid for some very local objective, that charge and discharge activity will have upstream impacts, and to the extent that it is the same need as upstream, that could be a benefit. So if you're doing peak load reduction from 2 to 4 p.m. on the distribution circuit, and that happens to also be the peak generation at the transmission level, you get 2 for 1. If the feeder level is from 10 p.m. to midnight, and the transmission levels from 2 to 4, now they're out of sync, and so you either might have to do twice as many charges and discharges, but you have to keep those different requirements in context with one another. So that's a simple example, but another one would be maybe if you're trying to do frequency regulation, going up and down, and you're down at the edge of the grid, that has the potential to cause local voltage issues depending on the state of the feeder and the topology of the feeder. So. Thanks.
Howard?
Just one. Yeah, just one. There have been a number of articles about the problems with the international supply of lithium and potential shortages. Is that an issue, or is there any other issue on the horizon that looks like it might push storage projects back?
I can comment on.
I'll just say lithium's not really an issue. There's maybe a little bit of a scale up that's necessary, but lithium's one of the most abundant elements in the Earth's crust, so it's very common and relatively low cost. It's more expensive than it was 10 years ago. As we ramp up, the more important issue is these metals like cobalt or nickel, heavier metals that do have more volatility in the commodity pricing and make up a larger percentage of the cost.
There's 2 ways to address that. early in the lithium-ion growth period, there was speculation that there wasn't going to be enough lithium, and then a lot of the companies that owned lithium mines that were presently shuttered at the time just opened them up to meet demand, and that issue went away. So you might see that a little bit on some of the precious metal markets. In addition to that, end-to-end recycling of lithium-ion is something that has been established and shown that can work. It's just a matter of getting market scale to get there. So the more lithium-ion batteries that you get deployed, the easier it'll be to start putting that back into the supply chain, just like has been demonstrated with lead acid. So that's a potential technical solution to that as well.
Yeah, another thing to consider is lithium-ion batteries are used in electric vehicles. Electric vehicles are now reaching that 5-year, 6-year, 8-year time frame where they're starting to think about replacing the batteries. When they replace the batteries in the car, they still have 80% of their useful life left. So is it something that we could turn around and use in grid scale storage? So if you can get it with 80% of its life left and buy it for 25 to 30% of its price, it could be a good opportunity as well. But again, as been presented by the other colleagues here, lithium-ion battery pricing keeps going down and down. So, both those two things are favorable.
Tom?
Scott, people have generators in their homes sometimes. Maybe they're gas generators that take over when the electric goes down. Is that a place for batteries?
Yeah, so when I talked about premium service offering with a battery, really that's the target customer. So that customer who says, hey, I have a more sensitivity to outages and I want to do something about it, their choices today are pretty well go get a gas generator. There's starting to be a new market for batteries. But how could we work with them to entice them to go to that direction where we can work together, where we both get benefit out of it? So they get the benefit of the outage improvement that they want, but we also get some control of that battery so we could use it for grid storage. So that way we're sharing costs and we're sharing benefits.
My other question is having to do with, this is such a large scale, I believe, like peaker plants or peaker power facilities. That we, that's part of the process. Is that going to be, is there a place for energy storage on that kind of size?
So we just published a study on, sorry, interrupt.
Yeah, okay.
We just published a study on that last year, and the main factor in driving that in the comparison is, first of all, the capital cost. So as those keep going down, it makes it more interesting and compelling. And the second is fuel cost. So if you couple the storage with solar, for example, can you make that a dispatchable peaker? It depends on the duration of the storage and the cost for that. And also depends on what kind of projections you put on your fuel cost by, say, comparing it to a gas peaker. We all think that gas is going to stay low and remain low, at least for the near term. But that's never been true. So, how much of an uncertainty factor do you want to put on fuel costs in the future? And if you look at the best case of storage versus the worst case in gas, it wins out today. If you compare median to median, gas still has an edge. But it just depends how you deploy it.
To build on that as well, I think from our perspective, one of the biggest opportunities for energy storage really is as a peaking asset. As Davion mentioned, one, energy storage at scale, 100, 200 megawatt size systems, even smaller, is competing on a head-to-head basis against other thermal peaking assets, over the next couple of years, if you look at something like an aeroderivative or a recip engine, for example. So purely just on installed capital costs, you're essentially at the same point. Second is the flexibility that energy storage provides. Its ability to respond very quickly, very accurately, becomes more and more valuable in a grid that has more and more intermittent resources and intermittent load or variable load in it. So for example, you get the same benefit, the same grid benefit from fewer megawatts of a fast responding resource like energy storage compared to a slower responding, more traditional resource when you're thinking about that kind of grid balancing, the ramp times, et cetera, that you need. So you're both cost competitive on an upfront build basis, but then each megawatt of storage is becoming more valuable as well. So absolutely, storage is practical at that scale and cost effective. And very concretely, we're building a 100 megawatt, 400 megawatt hour storage system to come online in 2020 for AES under a 20-year contract to Southern California Edison.
Great.
Jeff brought up this notion or emerging idea as distribution level storage as opposed to behind the meter. And I didn't know if anyone else could comment on that emerging idea that he put out there. I guess I'm kind of looking at Scott, but I don't want to put you on the spot either, so.
Yeah, so the distribution level storage is exactly the two use cases that I was, talking about, where, again, I think there's a great opportunity to solve reliability problems on the distribution side, capacity problems with an energy storage or a battery, so.
So you definitely agree that that is an emerging
Yes.
idea, and it's something that, but it's not, is it something that that AEP has deployed?
I mean, you could look at our Bluffton, Ohio battery
well.
and say that's exactly what that is. So that battery itself is served on the distribution line. It's right outside the substation, so it's a very perfect example.
Anyone else? No? Yeah.
Yeah, I would say in conversations, so I tend to focus on markets in middle of the country, east and northeast. A lot of utilities that are participating in PJM, New York ISO, ISO New England, a lot of wires-only utilities companies, for example. And I'd say across the board, those utilities are looking at distribution-level applications for energy storage for exactly the reasons that Scott discussed, is because it can provide value in cost deferral, because it can improve reliability, and you're seeing a lot of utilities taking first steps towards 2, 3, 5 megawatt projects to demonstrate that use case. But we expect that market to grow very, very quickly, and that application to grow quickly. I could imagine a world 5 to 10 years from now where energy storage is almost standard substation equipment, because of the benefits that it's providing to the grid.
Interesting.
So if I could add to that, I mean, that's sort of the point of what we were saying, is that you think storage, especially with a certain delineated set of functions and capabilities, starts to look like a general purpose grid component as fundamental as, say, a transformer or a circuit breaker at the distribution level. And so what I was suggesting is that that's the direction that you might want to look at in terms of when you're thinking about later on about what you're going to do in terms of guidance for modernization and so on, as to how much you want to think about that. You heard a lot today about different uses of this, and you heard a lot of things that were actually reflected back to the bulk energy system level. And it's a lot of times the services stuff tends to want to gravitate there because there are market mechanisms there that people see an opportunity to make some money with all of that. But what I wanted to suggest is that there is another thing you should think about, and that is not necessarily that you would market monetize those things, that it's some things that you would do to improve the inherent operation of the grid at the distribution level. And we heard some of that today. That's why that model matters too, as an additional tool in your toolkit when you think about this from a regulatory and rate standpoint.
I would just add that, some of the things I was bringing up in my presentation, that the tool set is still evolving for planners because the distribution system is so massive. It requires a lot of different eyes on the problem to figure out where these opportunities exist. And given that it's only been a very short period of time since storage really got into the cost range of interest for a lot of these applications, we're still at the leading edge of finding the cases on the distribution system and specifying them and integrating them into the utility control system. So I would say tons of potential for, stacking different functions and things like that. Probably some of the more challenging to access because of a lot of the enabling communications and controls that would help to, squeeze the most value out of those distribution level assets.
I would comment that the distribution model for storage, I'm not sure if we could say it's emerging. I would say it's happening all across the country in a lot of cases. If you see a non-wires alternative RFP that comes out, usually that's assigning, trying to find a solution for a distribution upgrade problem. There's plenty of developers out there that might not be biased towards behind the meter or in front of the meter storage, and if there's a means to pay for a project and develop it, then they'll do that at the distribution level. I think the APS project, the Iron Horse project, was a distribution feeder line. And so most of those are, trying to address a localized load problem, and that's pretty common, and so if it's like a 2 to 10 megawatt kind of solution, that's certainly possible.
Great. Thank you so much.
Quickly following up on Commissioner Johnson's questions. Has the industry developed a cost-effective battery for residential applications? And if so, does it capture data? And I guess, Scott, is it important to the utility that it capture data and transmit data, or don't you care if it's in someone's basement for transitive, I guess, if I understand it correctly, Jeff, application? So again, is there a cost-effective battery out there for residential?
Some people would point to the Tesla Powerwall. The folks at our lab have done some analysis on this that suggest it's still kind of pricey for residential applications. So I'd say that it appears that maybe there's still some effort to go in terms of cost reduction, but as has been talked about today, those curves are all trending in the right direction for that. In terms of the amount of data that they collect, I haven't looked in detail about that, but that's typically the way everything is done anymore. In fact, if there's anything, it's too much communications to devices that leads to cybersecurity vulnerabilities. So it would not surprise me that we'll see that capability incorporated, just because there's a desire to have aggregators and others be able to manage those collectively too, and you automatically end up with all of that capability when you go in that direction.
Okay, thanks, Jeff.
I guess also I'd like to add, if a battery, residential battery, if there's no control from the utility, no insight, no visibility, then it's just energy efficiency at that point. And energy efficiency is valuable, but again, it's just energy efficiency. If you can add to that battery where the utility has some ability to see it, control it, dispatch it, now it's a tool for the utility. So that's where where you add value to that situation.
Thanks.
Yep.
Scott, can you tell us whether your company has begun looking at or inventorying the substations for their suitability to accommodate, or whether they're constrained from accommodating storage of the type that you've described?
Sure. So to answer the easy part of that question is, do we look, how often do we look at substations and their capacity and how close they are to overload? We do that all the time. That's just part of our daily planning jobs. Have we turned the corner and said, okay, for this situation, is it a prime candidate for an energy storage solution? We have not done that in a formal way, but the planners or the engineers that are looking at this at a day-to-day basis, even though it's not like a formal program and we're studying it intently, there are engineers that raise their hand and say, hey, look over here, this might be a perfect example where we put an energy storage rather than a traditional T&D project. Good example of that is right now they're talking about a project in Marietta that would be, from what all I'm being told at this point, is a perfect example. We haven't studied it, we don't have any cost to benefit analysis yet, but those are the type of things that we really want to dig into deeper and say, hey, is this a perfect solution, and can we move forward with that energy storage solution rather than the T&D investment? So long-winded answer to say, we're doing it informally. We want to move that direction where that becomes more of a formal part of our process, and that's just something down the road.
Yeah, and I would just add, comment rather than question. So in a policy document, if we were to say that we are interested in adopting battery technology in front of the meter as a potential non-wires alternative solution, then that yields potentially two important questions, which is from a planning perspective, we just don't want to do it just to do it, right? We would need to ensure from a planning perspective, per Dan's question and your answer, that that is a sensible place to put it, first of all. And then second of all, we would have to feel comfortable with the cost-benefit analysis being conducted.
Right.
And so just, I guess, very brief question, how sophisticated are the cost-benefit analyses, right now? Does AP Ohio or do any of the other panelists feel like there is a very tangible cost-benefit analysis that can be deployed for this?
Yeah, I guess I'll comment on that. So when California they were investigating whether or not to put forward a storage target, they asked the California Energy Commission to commission a study, and we did that study. The way that we did that was we have transmission level cost models, we have distribution level cost models, and we can put in all kinds of assets in that, whatever it's a generating asset, a solar asset, wind, conventional generation, gas turbine, and we can put in storage, and we just put in the qualities of that. So we basically customized a model to fit their network, and we identified sites where they would have high probability of success for use cases, and we came out with megawatt recommendations for each of the 3 IOUs in the state, and that's what they put forward in front of the CPUC, and then that's what eventually ended up in the legislation. We didn't know it was going to go in the legislation. We were just putting those models together. But it does require fair amount of sophistication, understanding what the network looks like and where to put storage, what their projections look like for the increase of renewables in the state, for example. And that's a fairly significant effort. But that's the kind of effort that would be required under any study in any state.
So I'd add that EPRI was the other entity that did some of the work for California in 2013 as part of that storage proceeding. And since then, we've developed the tool that I mentioned in our last slide, Storage Vet, which is a publicly available model and methodology to do cost-benefit analysis for energy storage projects. There's 2 separate issues. There's the models, and then there's also the data. So sometimes it's maybe a challenge to translate kind of individual project analyses into the public domain, because some of those analyses do use some sensitive data sets. So I think that we're very close to having at least credible estimation of value and frameworks for doing these types of analyses, but there's still data questions, and then there's still details that can be worked out in various power flow tools and things like that the planners use.
Okay, Scott?
Yeah, as I say, it all comes down to how much data is going to be necessary to show that it's valuable to move forward. Again, we're all about making sure that there's enough data there to show that this is a worthwhile path to go down. But we don't also want to create a bunch of calculations that add no value. So we want to streamline the process as much as possible. Again, we're here to do the right thing. We want to show that it's the right thing. But again, we don't want this to be, a lot of just busy work, if that makes sense.
Sure. Okay. Anything else? Christina?
We talked about some of the potential benefits from the recent FERC ruling kind of in the wholesale marketplace. In a restructured environment and using kind of these resources as a distribution service, how do you kind of optimize that? And has it been traditionally that the utility would sort of competitively procure that? Or what are kind of approaches that have been taken in restructured environments for that?
To be continued. Maybe. You want to get back to us on that one? That's okay. Yeah, that's a very challenging question that you just asked this panel. That FERC order is relatively new, right? And so I think we're all collectively trying to figure out how to best utilize storage DERs in the wholesale marketplace. There's a technical conference that will be convened associated with this, so it's not that even FERC has all the answers as well. So it's okay if you don't know the answer to that one. Okay. Anything else from anybody? Thank you very much, panelists. Okay, wonderful day today. A lot of information downloaded, so thank you very much to our panelists. We are being educated as you educate us, so very grateful for everyone's participation. We will convene at 9 a.m. tomorrow for Markets Day. See you tomorrow.